Now that we know how to read a basic pedigree, we're going to talk about the 5 different types of traits that can be displayed in a pedigree. So if you remember, a pedigree can help us tell if there's Mendelian inheritance going on, whether or not that gene is located on a sex chromosome, either Y-linked to the male or X-linked to the female chromosome, or if it's on an autosome, and whether or not it is dominant or recessive. So therefore, the 5 different types of traits are Y-linked, X-linked recessive, X-linked dominant, autosomal recessive, and autosomal dominant. As you can see, these are the relative sections that go with that. I'm not going to cover them in the order of the book because this is the order that we will assess a pedigree. So I'm going to do it in this order in the lecture as well. So the first trait that we're going to talk about is Y-linked. And as the trait sort of entails, Y-linked is only found on the male Y chromosome. So this is section 4.6 of the book. The figure that you might want to look at in association with this is going to be figure 418. So this is only found on Y chromosome. And most of these genes, therefore, are associated with male development. There are not equivalent genes on the Y chromosome to this, so males are considered to be what is called hemizygous. In effect, this is a de facto haploid situation. You have 2 sex chromosomes, but they don't have equivalent genes at the same locus. So you only have one copy of these, and this is why males develop as males. There's no equivalent on the female, so females develop as females because they have their own set. And therefore, we're only going to see this pass father to son. And so in the pedigree, I'm going to draw one similar to what they have in the book, but you will see it. Father has it. Father must pass on a Y chromosome to sons, so therefore the sons will have it. If these sons have kids, then their sons will have it. So we see it pass father to son, and we see it in every generation. Y-linked is very simple, and when we get to try and discern pedigrees, this is the first thing that you'll look for, because if we don't see it, we can eliminate it, and we only have 4 other hypotheses. So in a sense, all of these different types of traits have become your de facto hypotheses. So if something is Y-linked, we will only see it in males. We will see it in every generation being passed from father to son. So next one is going to be X-linked recessive. Now this one has some history to it. This one we know a lot about a few of these traits. A lot of you may be familiar with color blindness, or balding, or hemophilia. You know, I often talk about the Tsar Nicholas II of Russia, and his wife was related to Queen Victoria. She was a carrier, and she passed it on to their only son. This is found mostly in males. The only time you get it in females is if dad is colorblind and mom is a carrier. So it is possible. We often say, oh, women can't be colorblind. They can, but it takes a very unique set of circumstances. But predominantly, we're going to see this in males. And so this brings up a new term, carrier. So a carrier is someone who has the gene, but not the phenotype. So mom, if she is a carrier, is not colorblind, but has the gene. And because it's recessive, it is masked. So remember we talked about recessive genes are covered over. They are masked by the dominant gene. So she has a dominant color gene that will supersede this. If you are a male, though, since you only have one X chromosome, you're also hemizygous for these particular genes because, once again, you only have one copy. So if a male has color blindness, they will display color blindness. So in our book, they give a figure for this one. If I remember correctly, they didn't give a very good example of an X-linked recessive. So let me just go back and check. Oh no, they did fine. So the key characteristic for finding X-linked recessive traits, and I'm not going to give you a tricky one with a female in it. I'm going to always show a typical one. I will leave the tricky pedigrees to your next class if any of you want to go on to become genetic counselors. And I'll tell you, if you want a lucrative job, genetic counseling starts at about $60,000. Don't get to give a lot of good news though. So in these, we will have moms and dads, and if they have kids, I have to think about how I want to do this. Let's say we end up with an affected child here, but then this person, I didn't get myself in a frame. Let's say this individual. They also have some kids. Actually, I'm going to do it a little bit different. I'm not going to make this person affected. Oops. So this person's unaffected. So let's say dad here is affected. And then all of a sudden, we see the trait show up in a successive generation. So X-linked recessives, the pattern we're going to look for. Do males only have it? Don't worry about the exceptions. And do we see it skipping generations? So I see it in the first generation, and I see it in the third generation, which means that mom must have been a carrier, and she must have passed that on to her daughter, and then her daughter passed it on to a son. So one thing we're going to always know is if we do see a male that is affected, we know that mom had to be a carrier if she is unaffected, because that's the only way that she would pass this on. In order to also show that you are talking about 6 chromosomes, and then in particular it is on the sex chromosomes, we will always use an X to denote that this gene is carried on a sex chromosome, the X-linked, and we will then superscript like we did for blood types. So this will be a way of showing that this is a sex-linked gene and it's dominant, uppercase letter, sex-linked gene, and recessive. We also know that males we will symbolically show as Y. So this individual has the colorblind gene. That is a recessive gene. So they will be X, little h, and then Y. This is why they're hemizygous. They only have one copy. Mom of this one has to have one dominant gene showing no color blindness, and they'd have one recessive gene that they pass on. This mom would also have to be heterozygous. Dad had to have the recessive gene. Because these males do not have color blindness, then they have gotten the dominant gene from mom and the Y from dad. But we still show it's a color blindness is a sex-linked trait. It's on the X chromosome, and they have the dominant gene. This male would also be the same. Dominant. Dominant. And even though this person came into the family not through relations, we know that they also have to be dominant because none of them are showing the trait. If you will have a dominant gene, it will mask over the recessive. Now this individual, we know that they had to get one dominant from dad, but they could have gotten either of those other two from mom, and both would show that they are not colorblind. We would actually have to look to see what their children produce to determine what their second copy is. So that's X-linked recessive. Only in males, skips generations. Nobody in this generation had it. And yes, it can occur in females, but I'm not going to give you that on a quiz or a test or exam. I'm going to give you the typical pattern. So if you're not X-linked recessive, you could also be X-linked dominant. If you are X-linked dominant, we're going to see the trait in both sexes. However, males will still skip a generation. So in this case, we draw a pedigree here. Let's throw in a few kids. This will also throw in some other individuals. Say this couple also had some kids. So in this particular one, let's also give some kids over here. It just makes it more interesting. So in this one, we would see the pattern of skipping generations in males, but we might also see it in females. Not necessarily all of them, but in some of them. So in X-linked dominant, you still are going to see that males skip generations, but females can occur in every generation. So both sexes are represented in X-linked dominant traits because it's a dominant trait, therefore it is going to be expressed if present. Therefore we know that this individual has to be homozygous recessive. They don't show the trait. The trait this time is dominant. So recessive, when you're not showing something, you have to be homozygous recessive. This individual would also be homozygous they wouldn't be homozygous, they would just be recessive because they have a Y. Now, we don't know if this individual, we know that they have one dominant trait. Oops, gotta put the dominant in there. And we also know that, well, do we know? We don't know, however, what their second one is. Everybody who has it has to have at least one dominant trait. Dad has to have it because he's showing it, the other one is Y. This grandchild has to have it because they're showing it, but the other one is Y. Females, though, we may not know what the second one is depending on what's there. However, this particular dad, we know that they are recessive and they pass on a Y, but to a daughter, they're only going to be able to pass on this recessive allele. So we actually know that they must have gotten a recessive allele from dad, and they must have gotten the dominant one from mom. We know mom has one dominant. Now, do we know what her second one is? Well, we don't, because they could have gotten a dominant one from either mom or dad. Mom could be heterozygous, so that one's still a little bit of a mystery. However, we know this one here, this individual, they don't have it, so they have a recessive trait. Because they're going to pass on a Y here, we know mom also has to have a dominant that she got from mom. However, we don't know what actually we do know what the second one is. Because, well, maybe not. Nope, that one's still a mystery. Although this individual, we know that they got at least one recessive allele from dad, so they must have gotten the dominant from mom. So we do know that this individual is a heterozygote. So here's how we can sort of play with these things in order to figure them out. But when you have an X-linked dominant trait, remember, dominant now means affected. Therefore, you have to have a dominant allele in every affected person. You may not know what the second one is, but you know that they at least have one dominant. If you are unaffected, you have to have recessive alleles. Because remember, it's X-linked dominant. This is now what it means to be affected. All right, that gives us all of the sex-linked traits. You can have Y-linked with the male chromosome, only seen in males. X-linked recessive, seen predominantly in males, but skips generations. X-linked dominant can be seen in both of our sexes. However, it is still will skip a generation in males. So another one that's very easy to determine and is next on our list is autosomal recessive. Because it's recessive, that means an individual who is affected has to be homozygous recessive. So they would have two recessive alleles. Because most people are heterozygous, this will often hide. And what you'll often see in the picture, it doesn't always have to be dad that's first. Mom can also be first in a chart. I know we get used to our typical symbologies. I do too. But if we were to show this pedigree, we might see an affected person who has to be homozygous recessive. And because we're not on sex chromosomes, we're going to go back to our typical lettering. So autosomals traits will just have your typical uppercase and lowercase. Only the sex chromosomes will have the other. But if you have an individual arising from two unaffected people, you know that each of these individuals had to have given at least one of those traits. So dad contributed one, mom contributed one, but dad doesn't show it, so he also has to have a dominant trait. Mom doesn't show it, so she must also have a dominant allele. So in these pedigrees, all of a sudden you'll see affected individuals arising from unaffected parents. And then we also know, therefore, that these parents all have to be heterozygous. Because the only way you can get there is if one individual donates one recessive allele, the other individual donates the other recessive allele. It also means now that this individual has 2/3 of a chance of being homozygous dominant and 1/3 of a chance of being, 1/3 of a chance being homozygous dominant and 2/3 chance of being heterozygous. Because if you remember from your Punnett square, if you cross two heterozygotes, you can be homozygous dominant, you can be heterozygous, or you can be homozygous recessive. We know it's not homozygous recessive because they are unaffected. So that only leaves three possibilities. One of those three is homozygous dominant. Two of those three would be heterozygous. So any unaffected individual that we can't determine has this kind of a ratio. So that is how a pedigree would look for autosomal recessive. That leaves us with one last pedigree. And that is autosomal dominant. Now, if you are affected, you have to have at least one dominant allele. And the key to this one is no distinctive pattern. This is the default. If no other pattern emerges in any of the previous four, then we're going to just say it is autosomal dominant. Those are your 5 basic traits, and those are your 5 basic patterns in the pedigree.